So some homeworks from 5.3. I assigned the following. I assigned number 140. And this was a divergence test. So the divergence test, let me write down what the divergence test requires, is you have to calculate the limit for n going to infinity of an. And then you have to show that if this is non-zero or zero. If it's non-zero, then you have divergence. So if this is non-zero, then we have divergence. Okay, so here's the example of 140. So we have to take the limit from n going to infinity of n divided by the square root of 3n squared plus 2n plus 1. Now this one, I chose this one because it might be a little bit harder to calculate the limit here. Perhaps, okay, what happens, of course, if I plug in infinity, get infinity over infinity, right? So that's obvious for everybody, I hope. Okay. The issue is, okay, although it's L'Hopital rule, and I could try to L'Hopital, it doesn't work that well. I don't know what you've tried. It's not a great thing to do because you're going to have to take the derivative of a rather complicated function, this function. And so what I want to point out is, we perhaps you don't remember this anymore from Calc 1. There's another method, and it's similar to the method of rational functions. Is the same method. It's basically divide by the highest degree term. So what do I mean by that? So let's calculate what the highest degree terms are. What is the highest degree here? Well, this, of course, is n. Now you say, oh, the highest degree is n squared, right? This one. But no, it's the radical. We have also radical. So it's a radical of n squared, which is just n. So in both cases, the highest degree term is n. So let me get rid of all these things that I wrote. And I'm concluding the highest degree term is n. It's obvious for the top, but for the bottom it is because we take the square root of n squared. Okay, so now we have to divide by that. So divide here. And then we also have to divide this whole thing by n. Now, what now? We'll say, okay, the top I see, that cancels, that's 1. But how do I at the bottom? Well, so that's where we need one intermediate step. So the top, I'll write it up here because otherwise I don't have a space. The top we know cancels of 1, but what do we do with the bottom? Well, that's now the trick is instead of, we want to bring the n inside the radical. And of course, when we do that, it becomes an n squared. And then on top we have 3n squared plus 2n plus 1. And this is the rule because if you take the radical of a fraction, then it's the same as taking the radical of the top and the radical of the bottom. The radical of the top would be this, the radical of the bottom would be that. Okay? And once I'm inside the radical, now the calculation, I still have to do the division, so let's do one more step. So I have to, inside here, now divide each of these terms by n squared, so I get 3 plus 2 over n divided by n squared, and plus 1 over n squared. And then the n over n squared cancels to 1 over n, right? I'm going to do this a little bit quicker. So we can cancel this one. Okay. And this means, therefore, that each time we have these reciprocals, they go to 0. If we plug in infinity, and so in the end, our answer is a 1 on top and radical 3 in the bottom. But this is not 0, and therefore it is divergent. That's the divergence test. Okay, but as I said, we're not going to use that test that much. But it is important to know how to calculate limits of these sequences, because that is something we're going to do a lot. And this trick here of dividing by the highest degree term is also something we're going to do next time. So it's a very important trick. Okay. The next one was number 155. We have the question was, is this convergent or not? And what we need to recognize is that this is a p-series. And so remember, a p-series is something where the general term looks like n to the power p, where p is the one that will give us the test. So what is p here? So here, let's write this as a true power. Well, it's a fourth power and a third root. That means 4 thirds. Please make sure that you understand how these rational exponents work. Otherwise, this problem is going to constantly cause problems for you. All right, so now once I did this, it's clear P is 4/3. And what does this mean? It's less than 1, and that means divergent. Okay? And so that's the trick. In the other homework problems, always write it as a pure power. I'm do one, although I didn't say it was assigned as I did assign it, but not as a special problem. But perhaps some of you were struggling with it, so I'll do number 157. That was n to the power pi, which is weird, right? But okay, why not? And n to the power 2e. The whole thing about matters is we have to write this as a single power in the denominator, which means how do you bring powers in the denominator? By subtracting. So n 2e minus pi. So now the question is, what is 2e minus pi, right? So that we have to, we know what p is. P is this power, 2e minus pi. But it's not immediately clear what we are talking about here, right? What number is this? So 2 times e is, no, that's not correct, sorry. So e to the power 1. Sorry, my calculator doesn't want to work. So 2e, that is 5.43, minus pi, which is 3.14. And without calculating, I see this will be bigger than 1. Okay? So just if you want to know what it is, it's minus pi, and it is 2.29, which is bigger than 1. So this means convergent. That's the only thing, but we have to check. Bigger or smaller than 1. Okay? So that was 157. And the other problems are very similar to that. It's very easy, actually, but later this is something we're going to use also again in the next lecture. So make sure that you understand what's going on here. And then finally, number 160. 160, this is the integral test now. So this means that you're going to have to integrate. And therefore, you have to know your integrals, right? All right, so the guy that we were looking at is 1 over n ln n, for n going from, n goes here from 2 to infinity. You want to say, why from 2? Well, think about it. Can you plug in 0 there? Can you plug in 1 there? No. So you are forced to start at some other point here. So that's the reasons why we sometimes start from different in this. We start counting from 2 or from other numbers onwards. Okay, so we have a function f of x that mimics this thing, that is x ln x. This is a continuous function. It is positive and it is decreasing. Not writing it down because, as I said, you can assume that all these things are correct, that they hold. Okay, so we have f of x, but what we need to calculate is now the integral from 2 to infinity. And why do I choose 2? Well, for the same reason. I don't want, if I have to integrate this guy, I don't want to have an endpoint here that is also problematic there, because then I would have an improper endpoint. And this is already improper. We want to stick to the only problem that's up there is the infinite endpoint. So, okay, so this is, let's write it as a limit. That means we replace the top by t, and then we have to calculate this. Now the question is, how do you integrate this guy? You might be tempted to say, oh, I late because the logarithm. No, it's a logarithm in the denominator. That's not in integration by parts. These functions have to be really nicely there on top without anything too complicated inside of them, which is not the case. But I hope everybody has figured out that this actually is substitution. So let's do, again, especially when you do limits like that, I prefer to calculate things, indefinite integrals first, and then plug it in. So I'm going to use, well, what is the substitution here? Now, you would say, oh, the inside function is this whole thing, but that's not really going to work well. And so this is a little bit weird one. You have to see it. And this is actually ln x, because the derivative of ln x is 1 over x. I have ln x, so that will become u, and I have 1 over x, that will become du. Well, 1 over x dx. Sorry, I forgot to write my dx. Good thing, because I have it. So, all right. So what it becomes, as I said, this becomes u, so this becomes 1 over u, and then the x, this guy here, that is du. All right. Now this is easy. That's the ln of u, and so u was ln x. So this is the ln of x. Why not? Okay. So let's plug this in. The limit for t going to infinity of ln of the ln of x between 2 and t. That's the limit for t going to infinity of the ln of t minus the ln of 2. Sorry, it gets a little bit. But what happens if I plug in infinity in here? Infinity, ln of infinity is infinity, and again, so this whole thing will be infinite. So we'll see that this is infinite. Now, if this improper integral is infinite, so this means that it is divergent, right? Infinite means divergent, then this will be divergent. That's how the integral test works. Okay? All right.